I think you can start whenever you
Shall we
want.
make it full screen?
Yeah, I don't know how to I don't know how to put this smaller.
And then maybe close. Yeah, yeah, that was good. And then close this. Oh.
No, but the problem is that let me, okay, now.
Perfect. Okay, can you hear me at the back? Okay, good. First of all, thanks a lot for inviting me, Francisco and Lydia, and the rest of the organizing committee. It's a great pleasure to be here in Lyon. Somehow it keeps coming back on my agenda to come to Lyon. I have been here a couple of times, passing by, going to Portugal, but finally I have a chance to stay here a bit longer than just one night and meet people and meet Francisco. So I met him first in Lisbon, where I was working long time ago, but I'll talk about it in a moment. Okay, if you you can interrupt me in this talk because it's 1 hour long. It's a summer school, so it's more like a lecture teaching. So you can stop me and ask questions along the way also, so that you don't forget at the end. All right, let's begin. And I hope people in the WebEx or Google Meets can also hear me well. If not, just leave a question in the chat. I guess somebody would monitor. Okay, let's begin. So many people probably do not know that gray zebra, one of the endangered species of zebras, are now almost extinct. There are almost 2,000, approximately 2,000 to 3,000 left in the wild. Just to highlight that these on the right, if you see my mouse, are the gray zebras, and on the left that just ran away are the plain zebras. And these zebras are one of the key species of the savanna ecosystem. Fall of these species would actually eventually lead to fall of the whole ecosystem in which they thrive. Now, the question is, as engineers, as scientists, what can we do about it? Right? So that question comes to mind. Maybe we can use the new kind of technology, the new AI methods, new machine learning methods, robotics, to answer some of these questions, right? To figure out what can we do about these, the decline of these species. So the first solution that comes to mind, if you apply this technology, is if you can understand the behavior of these animals, if you can figure out what they are doing, like if they are walking or grazing or drinking, and how they're interacting with their environment and all these things, if you can understand the behavior, then maybe you can answer some further downstream questions, like coming up with some policies, what to do with the environment, how to interact with other animals that live in the same surrounding, which are not wild species, but actually belong to the farmers, like cattle. Right. So now the bottleneck or the challenging part of this question is, how can you understand this behavior of animal at a very large scale? Because if you do not answer this question at a large scale, that is over a very long temporal scale, like over time, over years, over different seasons, and over very large areas, then you cannot come up with policies that are sound, that are actually making sense, right? So you have a situation which is decline of a population. You have possible way of addressing it, which is use of technology, AI, robotics, and so on. And then you have a bottleneck problem, which is that you want to do this, like understanding the behavior using this technology at a very large scale, right? So I've set up the stage for this problem that we are going to discuss through, or like we're going to look at various answers throughout the presentation. But this is the question that revolves around the whole time, right? All right. So now let us set up some concrete goals that will formalize this, all this verbose thing that I talked about. What we want to do is to estimate the position of the subject or the individual, and then also multiple individuals, the whole population. We want to estimate the pose of the individuals also. Pose here means the skeletal pose. So the position just means, imagine the 3D bounding box around the person, you want to the centroid of that bounding box. That's the position. The pose is the full 3D skeleton of the individual. Now with this pose, the idea is that maybe we can infer the behavior. So is it a standing pose, grazing pose, or walking, and so on? You can get that from the pose, maybe. Or maybe you have another method to get the pose from. We'll see that later. Then you also need the map of the environment, right? How the individual is situated in the environment, which part of the environment it is, whether it is vegetated or it is an arid zone or so on. Then you need the some kind of tracking of this subject, right? Tracking and following. Whenever there's a robot involved that is looking at the subject, finding its pose, you also want the robot to follow this animal so that you continuously look or estimate the position. You want to do it over large spaces, already mentioned, and over long term. Right? This is one of the most challenging parts of this problem. And then eventually inferring behavior and then understanding what causes this behavior, right? And the changes in this behavior. Why, for example, a population does not come to a certain part now and goes to another part for grazing. So this is the kind of change that has happened in the behavior. And what was the cause in the environment? What was maybe it was climate change related cause, or maybe something human-induced change in the environment. What has caused this change? So correlating these changes to the changes in behavior. Now these are the goals. What is challenging in this to achieve these goals? First of all, the environments in which we are going to operate are very hard to reach, right? This ecosystem that you saw is a very fragile ecosystem, and it is far away from any human settlement, right? So to reach there is difficult. Then, if that's difficult, then how can you set up things like very complicated robotics setup? That becomes challenging. These are sensitive environments. You also don't want to disturb much in this environment, right? Because this is what you want to save. Also, if you can imagine a situation where there is a disaster like earthquake, post-earthquake, this is already not both sensitive and hard to reach environment, right? The quantities we're talking about, position, pose, and so on, these are very difficult quantities to measure, right? This is not based on some sensor that is already available that you can use it, just measure the pose, position, and behavior as well. Then you need to do all this very quickly in real time on robots that are operating in the environment. So you need to do it on board and online. And this keeps coming up eventually that you need to have a large spatio-temporal resolution with this kind of estimation. So with this objective, with this challenging part of the objective and the solution, I'd like to quickly go through the flow of the talk and then talk about each one of them, of course. So first, I will mention a little bit about my background and research focus, what I've been doing for the last several years. That will set the stage of what I will present later. Then talk about two projects in particular. The first project is AirCap, which more or less just finished. And I'll give a bit of overview, go into some details of some technical details of some works within that project and some results. And then I'll talk about Wildcap, which is a project that we started more recently and focused more on animals. And then some recent results on the animal behavior inference within that project and with some outcome. Okay, so I am originally from India. I did my bachelor's in Indian Institute of Technology. That's not mentioned here, should be also. And then I moved to Lisbon, where I did my PhD in electrical and computer engineering. There I worked with multi-robot systems, especially with the soccer robots, middle-sized league. And that's first thing I have in common with Francisco also. And then after that, I moved to Germany at Max Planck Institute for Biological Cybernetics in Tübingen. There I worked more with aerial robots and teams of aerial robots as a Marie Curie fellow. And then after that, within the Max Planck Institute, I keep moving different institutes. It's like one big organization with many institutes. And so first I was research scientist and then research group leader at the Max Planck Institute for Intelligent Systems. That's a different institute. I'm still there. But now part-time, because from 2020 onwards, I got luckily a tenure-track professorship in the University of Stuttgart. And this also allowed me to basically keep doing what I was doing at Max Planck. So we focus on aerial robots, multi-robot systems, and perception for aerial robots. This is the revolving theme in my research. So the long-term research question that I want to address in my let's say, research group is how can autonomous aerial robots intelligently perceive, understand, and interact with their environment? It's a bit broad, but as a roboticist, sometimes you need to take the bigger picture to make sure all that you are developing actually makes sense for application downstream. So I think this kind of encapsulates my long-term research question. And then you'll see how I put that into perspective with different projects. So the focus has been on 4 different aspects of in my research group. And the first aspect is robot perception. What we are looking at here is how can aerial robots detect and track subjects on the ground or also in the air, and also do motion capture. So we have been pioneers in this thing called motion capture, which is to get the full body pose and shape over time of an individual, of humans and now of animals. So this is what we do in robot perception. Then the other focus is on robot decision making and control. Once you have perceived what the environment, humans or animals, you also want the robots to make some high-level decisions in order to do something like keep tracking this animal, or keep mapping the environment. That is within this umbrella of robot decision making and control, where the focus is a lot on formation control of aerial robots. Then a more recent direction that we have taken in the group is on robot learning. How can we use data-driven methods to do some control of aerial robots, especially new kinds of robots that you'll see in a moment, like an airship. And finally, all our methods I intend, or we push in our group, to implement on real robots. So a large part of our focus is on developing our own autonomous aerial robots and also ground robot systems. Okay, so let's jump to the next topic, which is AirCap, the project that we more or less finished this year and has been running in the group since I was full-time at Max Planck and then in the University of Stuttgart. So the goal of this project is to do human motion capture, which is human pose and shape estimation, in a scenario where you have not intervened with the environment. So it's a completely outdoor scenario. It can also be indoor, but we focus here on outdoor. It's unstructured, so you don't know the map of the environment beforehand, and you cannot put cameras in the environment. You can also not put any sensors on the human. And the goal is to get human pose and shape, skeletal pose and shape, somewhere. Then comes the solution part, that to do this, we will employ a team of aerial robots that can fly around and look at the person. And these aerial robots can have some sensors, which is also not a part of the goal. This is part of the solution. Then. And then these robots can somehow estimate the pose and shape. So our solution, as you already introduced, that we'll use aerial robots. The first part of the solution was to develop these aerial robots, because we found out that most of the off-the-shelf aerial robots are not fully accessible. You cannot control them. You cannot provide low-level control commands to most of these off-the-shelf solutions. Plus, one of the things that you will see in the next slides is important, that we save every image frame of the that we obtain from the camera. So we don't want to have a compressed video saved in only, but we also want to access every frame. To do all that, it was clear that we need to develop our own aerial robot. We use this platform from Microcopter, but we also put a lot of effort in designing the whole system to have an i7 motherboard on it. There is a GPU, used to be TX1, now TX2, and a frame grabber, which is 5 megapixels, and so on. I can talk about it offline also. This is a question.
With all this hardware, what is the battery of your?
Yeah, very good question. So the battery comes down to around 15 to 20 minutes, which is actually not a very useful thing for things like motion capture, especially for animals. But all these solutions come later on, like how we address that. Okay, so moving on. So I don't spend too much time on the hardware now. If you are interested, you can ask me later. So the next phase of the project was perception-based control. So this is the second phase in which we said, okay, now what we want to do in space is to collect images of the person, which is the subject we do motion capture. We collect the images of this person as best as possible, right? So as best as possible can be defined in subsequent slides, but the idea is to always keep the person in the field of view, to have some kind of optimal estimation of the person's position, and then optimal perception of the pose of the person, right? So the perception-based control part, then we split into two different parts, which is perception part and then the control part, right? So in the perception part, what we were focusing on is cooperative detection and tracking. And obviously, you needed some kind of detector to detect the person in an image, because if you're using an image without having a sensor on the person, then you need some kind of a detector. And then for that, we use a deep neural network-based detector. Then there were some challenges that we addressed there, that how to use this DNN-based detector, which is not your traditional sensor, in a tracker, which is a Bayesian filter-based tracker. Talk about that in a moment. Or we can already say a few more words over here. So one of the concerns over here was that we did not want to share images between the robots, right? It's like In this case, you have two robots, fine, maybe you can do that. But as the number grows, it becomes interactable to, in real time, transfer images and use these images to detect on every image in every robot. So the idea was to share some kind of a low-dimensional exteroceptive information, which is, for example, every robot detects the person, gets a bounding box, gets the position on the bounding of 2D pixel, and this is the only information that you share with all other robots. And then you estimate at each robot some kind of a fused or some kind of a cooperatively tracked estimate of the person, right? And another interesting thing that we did here in this part of the project was to develop some kind of a unified estimator, right? So the idea that each robot was not just detecting and estimating the person, but was also estimating the full formation, right? And also improving its own localization pose with this mutually shared information, because each robot is looking at the same person, right? So it can use this information that the other robot it has given about this person, that is the same person, right? So this discrepancy between the robot's own position and the measurement could be used in order to improve its own localization estimate. So this is a kind of a unified way of estimating the location of the robot and the location of the person, the estimate. Important thing here is that this improvement is only relative, right? So the whole formation relatively improves its position with respect to one another, but not globally, right? So this, the idea that I mentioned is not applicable to improve the global position of each individual or each robot and the person. Very well, let's see quickly some results of this method. What you see here is a big collage of views. On the left, I can play it again to explain. On the left, you have the views of the cameras, so each frame displayed over there. In the center, you have the Arbis view, where the estimate of the person and the uncertainty around the person's estimate, the detections, the errors in the detection, and so on, represented with the ellipsoids and so on are there. On the right side, you have these external views, so they have nothing to do with the method itself. They're just like showing you what was going on over there in the experiment. There are two robots which are tracking this person. These robots are more or less tracking some kind of a trajectory that is predefined with some waypoints. And the goal is they keep oriented towards the subject, and they do the cooperative state estimation of this person. What you see on the left side is the back projection of the estimated 3D position on the 2D image, the blue crosshair. So blue crosshair basically tells you how good you have estimated the 3D position of the person. Right, so there are multiple issues here, which is, okay, before that issue, I must mention that the bottom two rows or bottom two pictures are comparison of the estimation with the ground truth. So the red is the estimated X, for example, on the left side, and on the right side is the estimated Y position of the person, and the green is the corresponding ground truth. And the ground truth is estimated by putting some kind of a RTK GPS module on the person, and there's also something like that on the robot. But unfortunately, these are proprietary systems, difficult to access and synchronize precisely with our own system. So there's some kind of an offset you see over here. And also our own system, as I said, globally, we use GPS on each of the robot to have the localization in the global frame. We improve the local relative localization, but the global drifts also with time. So there is also some drift that you can see. So on the left, you also see in these images from the copters some kind of a bright part of the image. And that was one of the things that we did in this work, which is to, a DNN, a deep neural network, would take a long time to run on an image and get some kind of detection, especially when you're working with a Jetson TX1-2 kind of device on board. So, but you need like I said in one of the questions was, we need real-time estimation, right? So like real-time means 30 frames per second, or 30 hertz. To reach that kind of frequency at using a DNN is difficult. So what we were able to achieve at max was 4 frames per second of detections on a small region of interest of the image only, right? And that was enough to give us a tracking of 30 frames per second, 30 hertz. All right, so there is this distinction, I guess you guys are familiar with this distinction between the detection and the tracking. The tracking of the filter is happening at 30 hertz, but the detection is happening only at 4 hertz, right? And now, even to get this 4 hertz, we have to find out this region of interest. And this region of interest was the most informative region where the person is likely to be. And this is extrapolated from how you are tracking the person, and then you predict where in the image the person will be in the next frame, and then you focus only in that part. Because if you focus on the whole image, then it's likely that the DNN will not end up in a proper detection, and then you actually keep losing the person in all subsequent frames. So you are enforcing some kind of most likely region of interest on the image. All right, so this was all about this work, and some more details are here. I can also talk offline about it. Some of the work that we have been doing in this context of cooperative detection and tracking is within these papers. The next topic is, like I mentioned in this video over here, the robots were supposed to move with some waypoints and then look only orient towards the person. The one important aspect we have not dealt with is the robots could also move in a way as to improve this estimate of the person, right? So this is the control part. So we talked about perception, and now perception-driven control part, right? Now I'll talk about that. Here, the idea is that we want some kind of a motion plan for each robot in this formation, such that the estimated cooperative state of the person is optimal in some sense. Meaning, for example, the uncertainty that comes out of this Bayesian filter, this Kalman filter or the particle filter, whatever, this uncertainty is minimized, at least in the steady state condition. All right, so I'll try to go a little bit into detail and then leave some part of for offline discussion. So the objective here is to generate formation trajectories that minimize, like I said, estimation uncertainty, right? Again, it has to be done online, and it has to be done on board, and the same communication constraints. You cannot communicate images. So our approach here was to come up with a convex MPC-based decentralized formation controller, which will actively minimize the joint uncertainty. So it will compute control commands for each robot so that they move in using this control command, that or the waypoints or at a very high frequency, such that they minimize the joint uncertainty as perceived from those positions, right? As well as they have to have a dynamic collision avoidance between each robot, and also they should not collide with the subject. Even though we fly much higher than the subject, we try to make sure that we are never above the subject. So we assume that if there is a catastrophic failure, the robot might just drop down vertically. So we also don't want to be above the subject, right? So this is how we frame the problem. So the goal is now to have a convex MPC-based formation control. Now, the idea is that in your formation controller's cost function, you want to have this minimization of the joint uncertainty, right? We use some assumptions from the observation model, which is the Gaussian observation model or the noise model in the observation of the person, to come up with some kind of decoupling of this joint uncertainty minimization. Two things. First was the distance constraint. So as far as you go, the uncertainty keeps increasing in the whole formation. I'll tell you about that in a moment a bit more. And the second thing was the angular constraint, that the angle that any two robots subtend with, or the nearest robot subtend with the subject, has some kind of there's something prescribed about this angle, right? So if we decouple our joint uncertainty minimization into these two constraints, these two result in some kind of a non-convex constraint of, right? You have an angular constraint that could be non-convex. You have a distance constraint, and you have to be beyond a certain region and so on. And all this, also because you have this collision constraint, right? So this result in non-convex constraints. Now we want to embed these constraints, or we did embed these constraints as external control input forces in every iteration of MPC. So globally, we cannot say we will have an optimal solution, but locally, we will convert these non-convex constraints into a control force. So we use a potential field function to convert these non-convex constraints into a force, which we embed in the linear system dynamics. So now it's in a linear constraint only. And then we have a convex MPC formation with linear constraints that we can run in real time and have locally optimal solutions. So this was our formulation. Now I'll tell you about a little bit about how we come up with these distance constraints and the angular constraints. Any questions so far? Yeah.
It's just the restrictions. And when you talk about the formulation, what happened with all the environment? I mean, in the videos, you are like sunny day and so on. Do you control somehow the environment when you make this kind of task and your formulation or not? I mean, it has effects of wind, sun, and so on. Because it seems, I mean, the rate is quite awesome when you talk about.
Okay.
I don't know if everything is in better conditions than ever or.
So one thing I have to give credit to is this DNN-based method to detect works really fantastically. And if you fine tune it with some extra images from conditions that, I don't know, with not so sunny condition or dark conditions, or typically we don't fly in the rain because it's not possible. We saw that, oh, and another important thing, most of these DNN-based detectors work for pictures that you take from the front of the person. But we also noticed that if you fine tune with some more images that you take from an oblique angle, it quickly, becomes very accurate. The detection becomes very accurate. So all these environment-related issues like go into this DNN, and when that is working good, the rest is more, high-level estimation problem. Okay, so the one of the things that when you have a camera and you're measuring the distance of the person, or you detect the person from the camera, you have some kind of a measurement model. So how the noise increases with distance and so on. So it's a heuristic, very popularly used in the literature also, that quadratically with the distance, the noise variance evolves. We could use this, but we also made many our own experiments to get the true distance and measure and get the detections and fit a curve to get this noise model. Right, and that's the thing, that with distance, the error grows quadratically, but with the orientation and the azimuth and the bearing and the azimuth angle, these errors stay kind of constant, at least at a given particular angle. Now, with this observation model, so when I'm talking about radial distance, azimuth, and bearing, this is the spherical coordinate system, right? Eventually, we need things in the Cartesian coordinate system. First thing you do is you make these observation models through system identification, convert this into the Cartesian coordinate system, which again, in the paper you can see about, there's something called measurement condition conversion, which ends up in some functions that are like functions of the angle, of the bearing angle and the azimuth angle, right? So these are not just independent of the state of the copter or the state of the observer with respect to the target. So if these noise models, or if these observation models have these azimuth and bearing as parameters, you have to deal with that, right? And for that, our assumption, again, we come up with another assumption here, which is regarding the bearing and inclination angle, only in the steady state scenario, right? So steady state scenario is like we have convergent formation and when we are going along with the target, right? That's the steady state condition I'm talking about. And what we mean there is that the assumption we took over there is, in that condition, we are more or less always oriented towards the target, right? So the bearing angle is close to zero. So with this is one assumption. And the inclination angle, so one point to be noted is that we were never using a gimbal on the copter. So we were using a camera that was fixed to the frame of the copter. So the precise number was like 45 degrees to the horizontal, our camera was focused at, right? And with this condition, we can also have this fixed angle. So we now know the bearing angle and the inclination angle when we are in the steady state condition. With these assumptions, now we have an observation model, which now we can use for the joint uncertainty minimization. What we find out, and then comes the next step, how do you fuse this uncertainty. So you can also look it up. It's also very popular or very commonly used minimization technique in passive look or state estimation, not active state estimation. The passive state estimation is what are the best sensor configurations that lead to the minimum uncertainty, and which minimizes the determinant of the Fisher information matrix and gives you the sensor configurations. It turns out that for K sensors, let's say you have this 2 pi by K solutions. And in this case, for example, on the right side, you see for 3, we have this 120-degree angle that you need to maintain with the subject in order to have the minimum uncertainty. Important is that this solution is basically the same as this solution, where it's pi by K instead of 2 pi by K. But we also have to note that in this case, we have a subject that is not uniformly the same from all sides. You have a human, right? It looks different from the other side. So a better solution to take in the case of 3 robots was to look at it from all around. Right, so this is a case-by-case solution. If you have 3 robots, 4 robots, and so on, you will have a different angular constraint. And now you have the angular constraint over here. And the joint uncertainty now gets minimized when the angular constraint is satisfied. And now the remaining thing is the distance constraint, right? Because the uncertainty in the ellipsoid, the size of the ellipsoid grows as you go further. Basically, so as you go closer, it will be bigger. So that's the distance constraint that boils down to the distance constraint. Okay, so there's so much for how we come up with the decoupling of the uncertainty minimization into distance and angular constraints. And then what we do further is to convert these non-convex constraints into some kind of a force at every iteration of the MPC. And this force is in the linear dynamics of the system. All right, we can talk about the details as much as you want after the talk also, but feel free to ask questions. Now, what I have shown so far is the cooperative detection and tracking module, and I've shown the convex MPC-based formation controller, right? Now put them together, and every robot is basically running these 2 modules in addition to other modules like the low-level positions, yaw controller. Remember, the cooperative the convex MPC base is only about positioning the target with respect to the subject, positioning the robot with respect to the target, but not orienting, right? The orienting part is through a separate yaw controller that orients always towards the subject. You can also include it here, making it more complex, but yeah, that's the proof of concept, basically, in some sense. All right, so and then all these big boxes are basically each copter, and then they communicate between themselves with their own self position, so whatever they have estimated about their own self, and the target detection measurements to then do this cooperative detection tracking, and then use this information to decide where to fly next in order to minimize the uncertainty and the estimation. Okay, so this picture now summarizes the results of all the theory that I have explained so far. What you see here is this person moves from this position on the right to the left side. So this is a multi-exposure image, so many images stitched on one. And then the UAVs have reached the steady state condition, MAV 1, 2, 3, these positions. And now the person walks, and this is the kind of trajectory that comes out of the MPC, and the robots then do that or fly in that trajectory in order to keep the person's estimate optimal in that sense. Okay, I will skip, I think, a video for this because there are several other videos I'll talk about. But if you go to my website or if you look at one of these papers, you'll also see several videos that show you like these experiments. And also in conditions where we do not have this optimal way of tracking, and how these robots then actually form certain formations which also look a bit dangerous. They might collide, or they are not giving optimal results. An important thing here to note is that the formation has no predefined geometry. This geometry is emerging from this observation model, and then which is then fusing with the observation model from other UAVs, and then with the joint uncertainty minimization. All right, so now I have covered basically this lighter part over here, which is perception-based control. Perception control, robots are flying, person is moving, they are acquiring images every frame, and you have saved all the images. Now what? Now what you want to do with these images? These images are optimal in some sense, and that some sense was what is the best position, what is the best uncertainty or the minimum uncertainty in the position estimate. But motion capture, as I talked about before, is all about skeletal pose estimation, right? It's not about only the 3D bounding box or the 3D position of the person. This comes now, because now you want to estimate the pose of the person, right? Which you want to do through the images that you have collected so far from these copters. So this is a picture that kind of highlights the an overall scheme of this method, where you have 3 different robots, for example, and they have taken frames, or they have acquired frames, and these are the red bounding box you see here is the region of interest where the human was. Then we zoom in on it, and then you get some kind of a possibility to do key point extraction, right? So if you're familiar with this 2D key point, there's a vast community which is doing pose estimation on 2D pose estimation using key points. So they track the key points on the person or any individual, and that's your 2D pose of the subject. So that's what we employ first. And so we get, so this picture is a bit small. I hope you can realize that there are many segment links and joints on the person, which have been detected by this deep neural network-based method. Important thing to remember, in the second phase from here, everything on this part, everything is offline. Everything before was online. So now we can run very complex DNN-based key point detectors and get these key points. Now, if I have to summarize very briefly what the method does, is that you have some kind of a model of what the pose and shape should be, which let's say is given by this blue person over here. Now you can imagine T-pose or an N pose of a human, and you can imagine what the pose and shape could be, right? You want to learn some kind of a prior distribution of certain parameters that give you this pose. I don't know if it makes total sense without going into too much details, but it's kind of a, let me explain it a bit better, like easily. You want a function which has some parameters, and you want to estimate these parameters. And the job of this function is to give you the position of the joints of the skeleton in 3D, right? Now, one way to do this one way to know this function is if you had millions of data points, meaning you took millions of people, or one or several people many times, put them in a motion capture scanner room, scan them, get their actual position, pose, and shape, right? Now you have a ground truth. And now you fit some kind of low dimension function with some parameters, let's say 10 parameters. And these parameters kind of encode the pose and shape variation of these people. When you scan these people, you ask them to be in different pose and shapes, not just T-pose, right? So this is the function you know already. So this is what we have already done in many other works before, and we know this function, right? And this is the SNPL model, or the function, and kind of gives you the prior distribution on these parameters, right? So let's just call these parameters theta and beta. Thetas are these parameters for the pose, and beta is the parameters for the shape, right? Now the question boils down to predict these thetas and betas so that you get the pose, because the function is known. All you need to know, all you need to estimate from any picture is this theta and beta. Now, what we did here, since we have 3 different images, we formulate a certain least squares minimization, which is for each key point. So basically what happens from key points, you predict these thetas and betas, right? So for each key point, you have this error between what is predicted and what it should be. And then you minimize this so that what is the optimal theta and beta is coming out of this minimization problem. Okay? And then what we get here is basically the estimated theta and beta, which we put back into this function, learned function, and we get what you see in the red human pose and shape over here. When this is back projected on this image on the left side, you see how good the result is. It is not always amazing or the right thing to do, let's put it this way, that you back project and see whether you are true or not, because it can be true from this position or this viewpoint because you actually use this viewpoint for the prediction, but it might not be correct for other viewpoints. But the more viewpoints you collect, and if they are shown to be correct for all these viewpoints, then you know your method is functioning fine. Okay, am I still within time? Yeah. Okay. Good. I will slowly move to the animal case study and animal project. I hope I have not bored you so far. But yeah, so let's jump with few sentences on the results. So now you get the pose and shape from the images, right? So the first part I explained, you have an environment, you have humans, you fly the robots, you get the images. Now I explained that you have the images, and offline in your lab, you apply this method, a very heavy optimization method, get the pose and shape. But the original goal was that we wanted to do this pose and shape online, right? Not offline also. How can we do that? So one of the things that we did in that context was called AirCap RL, which is reinforcement learning based AirCap. Now, in the first part, I explained to you some kind of active perception based control, right? So there was a control that was doing something to minimize the uncertainty in the position of the person. Similarly, you can imagine now you want to do something actively to minimize the error in the pose and shape estimate, right? And how could you do that? For that, you need to have this kind of observation model where you are looking at the person from, and how the pose error would be from that viewpoint, right? So one way of doing that would be MPC, or getting to learn this observation model, making it much more complex. Another way that we did was a learning-based approach, right? So in simulation, we now started to learn using reinforcement learning to figure out what are the best viewpoints such that the pose that is estimated from the pictures from those viewpoints, these poses, have the least error. We do this in simulation because in simulation we can get the ground truth pose and shape, and you can know exactly what is the error in the pose and shape. So in this simulation, we have a simulated human, which is done by an artist, but with a high level of detail. So you have, and also animated, so you have the somewhat true motions of the person, but that's not the critical point. The critical point is that your detector could detect this person also as a person and also a real person, right? So what is, how good it is in detecting these synthetic people. Anyway, so in simulation, then you have these errors, and the idea, the reward is that you want to have as less error as possible between the pose that you estimate from the copter images and the actual pose and shape. So it turns out that we could, I'm not going into too much detail of this, but turns out that we could predict good trajectories. We don't know what is good because whatever the trajectories are, the results of the pose and shape should be good. That's the objective, right? So, and then we showed that with multiple up to 3 aerial robots, we could and apply this also the same thing, the same policy of these trajectories in real robots. That I have to mention that what we applied in real robot scenario was with only one copter and not with more than one copter. Okay, so there was one publication on this topic in 2020, and then we did not focus further in this direction, at least with reinforcement learning. All right, so I'll slowly move towards the animal case study and bring to your attention one video which showcases all this method that I've talked about, except the reinforcement learning part, the perception-driven control, the pose and shape estimation, in action, in a scenario which is a post-earthquake scenario with debris, and there are 2 aerial robots running everything on board and detecting and tracking the person. Any questions so far? I'll go a bit more deeper into this video also in a moment. So a few years ago, we had this great opportunity to collaborate with the Urban Search and Rescue School in Lisbon. They are actually one of the biggest schools in the world for this work. And they have a lot of scenarios like this, what you see in the video here, where you can do mock drills and tests and so on. So we were able to go there and work for a few weeks and test out our methods. And we also figured out several new problems, right? Like, for example, in this case, at that time, we could only do humans, pose and shape estimation, but we've also found out, okay, it is also very important that we want to estimate the pose and shape of the dog, even sometimes more than the human, because these dogs cannot have any sensors on their body. They can just run around and go in any dangerous place, a ditch or some sharp or near a sharp object, and can hurt themselves. And they cannot have a marker sensor because those become more dangerous if they go in such places, right? They could get stuck because of those objects on their body. So if we could estimate their pose and shape, we could come up with some method like warning using some kind of auditory signal from the robot in order to tell the dog to stop or to not go into certain areas, which is more dangerous. So this is a big problem for them, for the search and rescue people. And then the idea started to come, why don't we also start doing some pose and shape for animals, right? That is basically giving rise to the long-term outlook after AirCap. And this led to the formulation of the long-term vision of our group, which is to address the problem of biodiversity conservation. So it started with one animal, grew with lots of discussions with different teams and different people. And it has come down to this, to address the problem of biodiversity conservation through teams of aerial and ground robots that can intelligently perceive, understand, and interact with the environment. So part of the long-term research question is now with this application bringing this long-term vision. So this brings me to Wildcat, which is the next project I'll talk about, and I hope still keep you awake. So this is a sketch, partly. So the blimps or the airships over here are real. And the zebras are also real. And this picture I have taken, I've only put them together. So that's the only part which is the sketch. But I will show you that this is our vision, and this is where we almost are now. Now we are in the middle of the project, but we are almost getting to actually have this in reality. So then we can have a picture which is not a sketch anymore. All right, so by the way, this picture is of Brevi zebras taken in 2019 in my first trip to Kenya to figure out, again, as Francisco was telling you, go to these places and figure out, okay, these are challenges and problems that you did not know about at all when you were just sitting in your lab and trying to come up with robots. Then you figure, oh, wow, there are such big challenges that none of the robots can solve today that exist, right? So this gives you much more energy and motivation to come back to your lab and work on new problems. So we came up with this project idea, which I want to describe very briefly now, in Wildcat. Well, at some point we also called it Wild Lab, but yeah, it's one and the same. So idea is like, how do you want to monitor, or how do you want to do this pose and shape estimation or monitor the behavior of these animals, going back to the first question, over long temporal scales and large spatial scales. So our solution to this is, why not have a large aerial robot, which is here in the middle, which is an airship, which is too big enough to carry a lot of payload. So it can carry many small aerial robots, many small multi-rotor drones that, and it can carry around, and that it can deploy. And these multi-rotor drones go close to the animals, perform the behavior estimation and inference, and then they're depleting their battery. They go back to the airship, and this answers the question of Francisco, what he has talked about before, where if you have 15 minutes of battery time in your drone, in your multi-rotor drone, you want to expand its battery life. So in this solution, you can have as long as possible operation if you have many such drones being deployed and docked as your battery is depleting and recharging, right? And this big this big blimp over here is solar powered. It's also not science fiction. It is actually there already, and some companies are making this kind of blimps or airships. And they can loiter over the whole large space as much as possible. They can have a high resolution camera to look at the populations, not individuals maybe. And they can figure out where they need to go, stop, and deploy these drones. And these small drones then go closer, figure out the behavior, so sample their behavior, come back, and continue the mission. As a first step of this project, we also decided that we want to have some kind of a ground-based station instead of just starting off with an airship, so we can demonstrate all this, deploying, docking, whatever, from the top of a ground vehicle. All right, then the challenge, the end goals that we want to address through this whole system is, number one, individual recognition, that we want to identify each individual animal by name, right? We want its position, all that I talked about in the first part of the perception, cooperative perception, and then control, perception is control. Then we want the 3D pose and shape. What I showed you for humans, we want to now do for animals. So get the question also, there are many reasons why you want to do 3D pose and shape. Maybe you get behavior from it, maybe not. But maybe you can get other things like the health state of the animal, right? So in the case of cattle, for example, you can infer some kind of a health state from the pose of the animal. Like one thing that I know, at least now, after a lot of discussions with veterinarians in Hungary, I talk about Hungary in a moment, that the shape of the animal, the back shape of the back of the animal tells you how healthy it is. And just by looking at the animal, my collaborators were able to tell this is not going to survive, or this is the most healthy animal. And it was so amazing if you had one drone just going around in this wide, vast landscape, looking around and telling you have 100 healthy animals and 5 are unhealthy, you need to treat them. Instead of the people who are working there taking like several days to figure out which animals are unhealthy, and by the time they reach there, these animals are already dead. So this kind of things that you can come up with 3D pose and shape. Then you want the individual behavior. Comes down to why you want some kind of a policy in place for survival of the species, basically. And then group behavior, right? From individual behavior to group behavior. In this project, we assume that we know some kind of a map of the environment through satellites, and the map is not very super in like high resolution. Typically, you want to know the vegetation, density, this kind of like say high level attributes. All right, so I tried to go like color each one when I talk about them. So the first thing that we did was airship control. So we built a simulation for modeling and control of blimps, and especially connecting it with ROS, because in ROS, so in the robotics community, there are very few people who are actually interested in airships. Forget airships, I think there's nobody doing airships, only blimps. So blimps are basically these small airships without a superstructure. Few people are doing that, also only indoor. So it turned out that we had to develop a lot of things on our own, including the model in gazebo, and simulate some kind of a wind scenario for these, because these much more than multi-rotors blimp is affected by wind, right? And so we had to simulate that also. And then so we had this work presented in IAS in 2021, which was about simulation control of deformable airships. Now it's all very very well accessible for the community that is using ROS especially. All right, so very briefly, I jump to what we have been doing with formation control in this context. You see in simulation, at least one of our recent works where you can visualize how the blimps can loiter around a person moving in a rough terrain. So this is a gazebo environment. I will show you some videos of actual blimp, but it's important to note that a blimp is a very human labor intensive robot. For one blimp, you need at least 2-3 people, also a dedicated pilot all the time to control it. So flying 3 blimps is a huge task. Even though we have now 2 flying blimps, it has been very difficult to actually fly them together and do an experiment. But for proof of concept, we have done extensively in simulation, but flying 1 blimp at a time in real scenario. Oops. Is there a possibility for sound? Try. Okay, there is.
Our blimp is a relatively safe aerial platform compared to multi-rotor vehicles. It has 8 independently controllable actuators, a bottom-fed lateral thruster with forward and reverse thrust, servo-actuated top and bottom rudders, as well as left and right elevators. Left and right main thrusters capable of forward and reverse thrust, where thrust direction is adjustable with a servo-actuated joint thrust vector control axis. It has a mass of 10 kg, including a payload of approximately 1 kg. There's dynamic deformation in response to aerodynamic and control forces. Our blimp is suitable for deployment under harsh conditions such as sub-zero temperatures and wind up to 14 knots. We have developed a framework for simulation and control of such airships that involves several characteristics like changes in the blimp's rigidity and wind gusts. Using hierarchical PID controllers, we have developed a guidance and control method for autonomous navigation of our blimp. We have now developed a model-free reinforcement learning-based approach for blimp control to address challenges in the blimp dynamics, which are inherently nonlinear, time-delayed, and difficult to model.
All right, that was my senior PhD student, Eric Price, who was narrating this. Yeah, so this showed some of the first experiments until what we have been doing now. We have also a new blimp superstructure and a new blimp structure, and that we have experimented with in the last months. Yeah, maybe there is a picture at the end, otherwise I will show you like separately from this talk. Okay, so some of the blimp-related papers are highlighted here. If you're interested, please have a look at them. Except for 1 or 2 in my whole list of papers that I have here, all of them are open access, so you don't need any special access code or whatever. Okay, so let's move on to 3D pose and shape. Now we have the blimp. Now we can have a camera on the blimp. It can track the animal. It can detect and track the animal using the methods that I've talked before. It can follow the animal. I've not gone into the details of the formation control of the blimp, but it's one of the papers that I mentioned before. And now we get the images. We can get the images of the animals, right? So what are we going to do with that? Turns out the first question again comes to one of the things that Francisco asked before, was how do you manage a different environment? Now in the environment, the subject has changed. Now you have a zebra. Turns out that it's one of those cases where these DNN-based detectors are not working out of the box that easily, because for various reasons. I mean, for humans, there has been a lot of research and there's a lot of data out there, but for zebras, not so much. And even if there are some pictures, turns out that these pictures are like pictures of the picture. So the zebra is painted on something, and people have taken a picture of that, and that's been used to train the zebra detector. And so what we did was, actually we did 2 different things. One was like strike a collaboration with Wilhelma. It's one of the biggest zoos in Germany and probably in Europe, in Stuttgart Zoo, popularly called Stuttgart Zoo. They're also very keen on conservation activities. And then I was very lucky actually in this case to get the contact of the director, or the deputy director, I think. But the point is that she is also the coordinator of the equids in Europe. So equids, all animals related to zebras and donkeys and horses. Whatever happens to these species at an official level has to be through this, let's say, committee, and she's the head of the committee, and she's working at Wilhelm. So it was a great opportunity and great collaboration. We started. The first thing we did was to collect a lot of images in the zoo from an aerial viewpoint, as you see in this picture over here, and then fine-tune our detectors for the zebra using the data over there. So it worked with a very high accuracy. The second thing we did, which is not in the slides, but I can mention it, was we started with some synthetic zebras, which was done by artists in a simulated environment. and using with different pose and shape, right? And we used this test bed to collect a lot of images from different viewpoints and different distances and so on. And then we train our detector using only this, and we find out that the detectors for this are like resulting in super accurate detections also on real zebra images, all the zebra images that we have from the zoo, and also later on what we did in Kenya. You'll see that in a moment. The second animal that we got very interested in was the Przewalski's horses. I don't know if you see or realize that there are horses in this picture. And there are, I think there are 300, I hope, because typically the 300 is a number because in Pentazug Reserve in Hungary, there are 300 wild horses. These wild horses are Przewalski's horses. And that they started this project about 25 or 30 years ago. And the idea is that they kind of resurrect the species, which is now gone from the wild, to as a breeding program over there, and then act as a birth ground, let's say, for rewilding Europe and Asian plains with this species. And they have been super successful. So they have several locations, also in Spain, I think somewhere between here and the northeast of Portugal. In this region, they have also introduced Przewalski's horses. And interestingly, they have introduced it not in the plains, but some hilly regions. And in Portugal, in Italy, in France, not in Germany, in Hungary, of course, it's the main, in Romania, and all these places, they have like super success in rewilding landscapes with wild horses, and a lot in Asia. So Kazakhstan, Mongolia, these are the main places. And this place in Hungary, the Hungarian National Park, is the core place which is doing this, and within that is a Pentazug Reserve, which is a large part, which is fenced. And this allowed us, this was the perfect place where we could develop all our systems for tracking animals over large spaces and time, because we have a fenced area where we know the animals will exist. And we more or less know where the animals are in this large area also because of these people working there. They know the behavior of the animals, which season, what time of the day, where they are, and so on. And they were really kind to not only start out this collaboration, but also really actively be involved with us in finding out the problems and developing solutions. The other thing is the Przewalski's horses are very similar in behavior to the zebras, the Grevy's zebras, how these individuals interact with other individuals, how they are forming groups and harems and so on. And so since they are very similar, and they are closer to home, closer to Germany, it allowed us to, go there more frequently, do experiments and so. Because if you want to go to Kenya, there's a huge amount of bureaucratic process, mess, and taking your equipment, doing experiments over there. And also the animals over there are really in a dangerous situation. Here it's a much more not a dangerous, but it is a much more controlled environment where you can do things the way you want without the danger of poachers and so on. Anyway, so this allowed us to do more experiments in Europe, so in Hungary. And the things we started to do was, of course, first a lot of data collection, because we wanted variability in the number of individuals, because remember, one of the things we want to do is to do individual recognition and pose and shape and so on. So we wanted variability in number, pose, and background, multiple observations of the same individual so that we can see it from different orientations and times of the day and times of the year, because this wild horse is actually getting a coat during winter and then removing its coat, so it looks completely different. And one thing was very interesting that I found was when we went close to one of these individuals, I saw stripes on the leg, and I said, "Oh, zebra is not the only animal with stripes. There are more animals with stripes." It turns out there were more animals with stripes 150 years ago when they were all killed off in southern part of Africa. But actually, there is a Somali wild ass which also has stripes, but it's almost extinct. But you can see them in zoos. And yeah, I'm kind of distracting from the topic, but I just want to mention that it's important to mention because I am working with a biologist who's an expert in zebras, and he's still, after 40 years, he's not sure why there are stripes on zebras. question which every kid asks: why zebras have stripes? So the scientific community still has no consensus on why zebras have stripes. There are many hypotheses. Some have the highest weight, let's say, at the moment, that there is about parasitic attacks of fleas or something like this, and so they kind of get dazzled, or it is to dazzle the predator. And there is one more theory that people or some scientists are exploring, which is it allows them to maintain some kind of a temperature on the surface of the body because of these little eddies that go on with, because of the black and white stripes. There's a temperature difference between the just above the black part and the white part, and this lets some kind of circulation around their body. And this allows them to cool a few degrees more than other animals in the same environment. Anyway, let's get back to the discussion here. Yeah, so we did this data collection also with multiple drones so that we have multiple views. So remember, we're talking about multi-view pose and shape estimation. We want to do the same with animals. So we collected multi-view pose, multi-view images of many individuals and so on. And very quickly, some of the results. So same ideas of human pose and shape estimation. Now we are applying for animal pose and shape to see whether that applies or not. First, we had to, remember I talked about this crazy method to get a prior probability distribution for all possible human poses, that you put a human in a scanner, get this pose, over a large number of individuals, that you cannot do with animals, right? So that's a long-standing problem, long-standing in the last 10 years, let's say. Somebody did that thing with toys of animals. So putting toys of animals in the scanner and getting a prior distribution of the pose and shape. It's not accurate. It's not even good enough sometimes, but it's a good place to start. And now we are looking at new methods that maybe does not require this kind of prior distribution, or maybe we can learn it from some other technique. For example, the one I mentioned in simulation, right? So in simulation, maybe we can have different poses and learn some kind of prior from there. Same method, but different animals this time. Now Przewalski's horses. This is up close, one of the Przewalski's horses. A little bit frame by frame, so there is no temporal smoothing happening over here. Here is what you see as a 3D view of this estimated horse. Here's some failure case. So one of the hypotheses is that our hypothesis is that we can improve this if we are looking at the animal from different viewpoints, which makes sense, and that's what we are working on right now. So what we have done already is the blimp, the location, georeference location, 3D pose and shape. Now let's look at the behavior. So yeah, I'll go a bit quick. I think I'm really close to the end of my allotted time. So to do this animal behavior estimation, one of the things is you cannot just rely on the data from the zoo, or also from in Hungary. Yes, you can rely on some, but the true behavior for in each species and different individuals, like in what they actually do in the wild, can only be obtained in the wild. So we had to go to Impala. This is Impala. This is Kenya, where we went a couple of times, or 3 times now, to collect data and to experiment with our methods. And this is the kind of data that we get there. So you see, these are Grevy's zebras. This is an aerial video data set that we created. Many such videos, multi-view videos synchronized in time, to improve our detector, yes, but the most important thing is to infer behavior, right? So what would you do? Like, the solution that you would come up with is you start annotating some behaviors from this big data set, right? And then use that to train some behavior detector, and then use the detector to see whether you are getting an accurate inference of the behavior or not. This is our basically pipeline, which is implemented on the data set that we collected, like these kind of data set. Like, this is the multi-view, that was single view. And without going to details of the pipeline here, so the idea is that we start off with some data, we annotate it. So a biologist annotates it. This is a very important thing, because we cannot have an Amazon mechanical Turk doing this, because there are certain subtle things that only biologists and experts know what behavior is what. But so that's why we built this pipeline, which kind of gives some kind of a positive feedback to the detector that trains using this kind of annotation, and then again allows automatic annotation and presents it to the annotator, so that the annotator uses less and less time every next frame and every next video, right? So I almost end now with the results of this work on behavior inference. And as you see, after all this pipeline, we ended up with a behavior detector that gives these kind of detections or inference of behavior. So the purple ones are grazing, the red ones are standing, yellow ones are walking, and there is also green, which is running, but there's nobody running here. So this is the kind of decision that you can make using the method that we have developed. All right, so we're getting close to all that we have wanted. Starting from pose, individual recognition I didn't touch upon, but that's also something that we are doing. Pose, shape, behavior, and having the blimp up there. So eventually, what do you also want to do with the behavior? One of the things, like apart from making the policies for sustainability and so on, one of the things that we immediately want to do is to include this behavior inference back in the drone, so that you have some kind of behavior adaptive UAV flight, right? Which is, if you go and collect data of animals using a UAV, you are for sure disturbing the animal. You're for sure disturbing their natural behavior flow. But there is a way. If you can estimate this behavior and the changes in behavior, and kind of find some kind of mapping between your actions, like how far you are from the animal, how much you are accelerating, what is your noise, like auditory noise from the drone, corresponding to what is the change in the behavior of the animal, right? If you can learn this kind of mapping, then you can put this information back in the drone, and the drone knows that if the species are these elephants, I should not go a certain distance from them. Or zebras, gravy zebras. We found out the gravy zebras are extremely not shy at all, but the other zebras are very shy. So these kind of things we found out, and we have to do this more systematically and statistically significant in some sense, and then put this information back in the drone for some kind of behavior adaptive flights. All right.
In these videos,
Yeah.
The drone, could you tell me more or less at what height are you working, and if you are using optical zooms or something for avoiding these turbulence?
Good point. So the height varies from 6 meters to 100 meters.
Okay.
I cannot tell you exactly frame by frame here, but that is in the telemetry logs that we luckily have. So every frame gives us like almost the whole telemetry. The other question was
No, it's just to know the height and if you are using any kind of hardware adapter or optical.
Oh yeah, no. So the one thing to mention that all flights in Kenya were done by off-the-shelf drones. So DJIs and Anapis. DJIs, off the record, I don't want to recommend DJIs, but I want to recommend Anapis because they give telemetry per frame embedded in the video stream. So this is like the best you can achieve. All you need is the video, and you can run your, I don't know, whatever decoder to get per frame all attributes, like, I don't know, even the gimbal angles of the camera. So we use that. One assumption, which is very valid in that place, is that the ground is flat. So you can assume that, and then you know the distance with some small error to the animal. Because you know the angle of the camera, you can detect the position of the animal in the bounding box, and then you assume flat plane, and then you know the altitude above the ground level. So I think they're using time of flight and maybe some optical flow to get the altitude. But what is more reliable is the altitude that comes out of the GPS. And I can show you a plot. Like if you start with your takeoff point, and then you monitor the change in altitude, that gets you much more correct altitude. What you can also do is to put it in a filter, get this global altitude with the altitude above the ground, and get some kind of an altitude estimate. I have to note that this is important because sometimes you're above a plant and then you have a wrong altitude estimation, right? So that's important. Okay, I will skip this, I think in the interest of time, and I will go straight to the thanks slide to my team. A couple of postdocs now, PhD students, researchers, and Rahul just finished now almost 2 years ago. And my current affiliations and collaborations with lots of universities and non-university research or national parks, zoos, and so on. All right, I will end up with a little video, which you watched in the first slide, but this is a longer version of that. I hope it is not very choppy. I think it's fine. So what you see here is like one animal got a little bit disturbed, right? And it just like started running behind this one. And now it is again more disturbed. And then all of these animals, and notice that these are different from the others on the right top. These are plain zebras with a stripe pattern, which is very different from the grays. And so it is interesting that these animals were spooked while the others were not. Interesting for me, not for a biologist over there, because they know that these animals are more shy. And you see how they just broke off the joint group and went away, right? And why they did this, because this was a part of an experiment that we were doing. And now you will see. So my collaborator, Dan Rubenstein, like 500 meters away, he started walking towards this big joint group. And he just wanted to show me, demonstrate to me, that when I walk towards this joint group, it will be the plains who will run away and the gravies will stay. And typically, he has not used drones. Like now I'm collaborating with him, so we use drones, but he has this knowledge from manual observation on the ground. And now we can analyze this more statistically in a long-term way and more accurately using all the information that we get from a drone. So this was just to estimate what kind of things we can achieve. All right, and that was us flying the drone. Thank you.
Thank you very much. Are there any questions?
Sorry, I went above time.
Okay. It was very interesting. For me, I'm interested in the vision model that you use, because you told us that you were computing the prior distribution, but are you using some models like YOLO, like?
Yeah. So yeah, exactly. So this is what we use for detecting the animal or human, right? YOLO. I think at that time we were using SSD multibox, and that gives you the bounding box above the person, and then we use a key point detector, right? Don't remember, there were a couple of
Maybe a pipe, maybe, or
spin. There was one detector. There were a couple of detectors, that key point detector that we use on the image to get these 2D key points, right? And then what we formulated was, from these 2D key points, you get the pose and shape through triangulation, right? But this prior distribution just tells you how likely it is to be in this pose, right? And that's it, nothing more. It just gives you a model of, so there is this skeletal model, which is a kinematic tree, and that gives you a probability distribution over the positions of the joints.
okay.
Right? And from these 2D key points, then you do triangulation, and then you get the 3D position, right? And then you compute the error between what this joint model, or with what this probability distributed prior model gives, and what you get from these 2D predictions, right? And then you minimize this in order to, basically what happens is you see these 2D joint positions moving until they minimize the errors between what is predicted. So, okay, one more thing over there. So you have this joint model, joint distribution, which you can expect to project on a certain camera image, given the position of the camera.
I see.
You see what I mean?
Yeah.
So the error that you actually compute is between what you predict from this 3D model and what your 2D key point is giving. This is the actual error.
Okay.
And this is what you want to minimize. And the free variable here is the parameter of this distribution, right? And you keep changing this parameter, then you you change the shape, and then the projected 2D key point will be different, and will keep on changing until it matches the exactly. So the exact error is between the 2D key point, which is kind of a measured 2D key point on the actual image, and the predicted 2D key point, which is coming from a virtual camera looking at this 3D model. And what you can flexibly, like, what is the optimization variable here is this, changing this model.
Okay. Thank you. Yeah, it's complex, well, because you are working with 2D and 3D and everything. So thank you. Yeah, I see what you do. So any more questions?
When you are studying the behavior of the animals beforehand, in order to help your controls in your drones, which one is helping you? I mean, vets or people from there? I mean, how do you discover the real behavior of the animal? Because, for instance, for us, it's easy to understand the flock in a sheep. You know, the cattle is moving always to be together, to be warm, and so on. But here, we just know that some of these zebras are moving quick, spooky, another no. You discover by your experimental approach, or someone is telling you how should you interact with this animal.
Yeah, so this is exactly what I wanted to show with the person who was walking towards the zebras. His name is Dan Rubenstein, and he's the world's top zebra expert right now. He's working with the zebras for 40 years. He spent his life in Kenya, basically, and he knows. He wakes up in the morning, he looks at the weather report, and he goes out and he knows, okay, he should go to this part of the Impala Conservancy because the animals will be there. And then we go there, and then it's very likely the animals are there. And then he looks at, I don't know, footprints and whatever, and he knows what's happening. He's first time I met him, my reaction was like, this is National Geographic in real time happening. So it's giving me the commentary. So when we were recording this, we were also recording his voice, because that was that's I think that answers the question. And the same thing, not that great level of detail, but happens in Hungary also, because people working there have been working for very long, and they know the behavior of the wild horses, and they know them so well that it was only because of them, one or two of them sometimes, that we could go like walking between these horses. So this picture you saw, like with many horses from the high vantage point, we were in the middle, and it was a very dangerous. Like a person who's not an expert with these horses, how they react and whatever, it will be very dangerous to go there. But we were able to do that with this person.
Okay.
Does this person that works with zebras think that the fact that the UDAs are in there means that the behavior of the zebras changes in any way, or not?
Yes, he thinks absolutely. So we together have been looking at the video footage a lot, and he said that this many times this is not natural, and we can also easily see that when we are approaching, there is a point where one of the zebras looks towards the source of noise, which is the drone. And then we know the zebra changes its behavior because we have done something. And what we have also observed is sometimes when we are approaching, it's not exactly the reason, or the distance sometimes is not the reason, but when we stop, and then there is a change in the noise, right? Because we accelerate or decelerate or something like this, and that is what changes the, or makes the animal attentive. But also there are more subtle things that he has noticed, that one animal is affected. So one animal looks up, and somehow this information passes through the whole herd that, okay, there is a noise, but it's not very, aggressive. It's not going to affect us in some way. So the others continue to do what they want to do. And and we also noticed, because then we were like tracking these animals, is something that from a ground vantage point is difficult to evaluate. or observe is that how nicely they switch roles. So sometimes there's seven, something like this, 7, 8 animals, and there are 2 always on the side, looking for the predator, always attentive, walking and head up. And then they are like mowing the land. So they are just moving, going in a certain trajectory. And at some point, somebody in the middle just goes out, and this guy goes in. And so they change roles, and now this guy is now eating, and the other guy is looking out. And so this happens cyclically over a long period of time and trajectory. And this is something that without a drone or this kind of observation, it was impossible to figure out, like how the dynamics, the individual dynamics evolves over time, what they are doing, and which animal takes the role, whether it's a male or female, or bachelors, something like this.
So thank you very much again. Now we have a small coffee there.